This task, called Fortune, was a mix of reversing and web challenge. It had only 13 solves and was one of the least solved challenges during the entire CTF. The description says, "This website uses a state-of-the-art AI algorithm to find wisdom that fits your needs. Now it's gonna be easy." Let's click the link and see what this AI-driven wisdom looks like. It looks like a fortune-telling page. We can pick a category and get a quote. Alright, enough playing around. Let's dig into the code. Opening DevTools, we quickly notice a WASM file. Alongside it, some JavaScript calling function from WASM, get categories and get fortune. Let's download the WASM file and open it in Ghidra. By default, Ghidra won't recognize it. But with the right plugin, it parses just fine. After the initial analysis, we spot the expected functions and one extra, GetFlag. That becomes our next point of interest. Its code looks similar to getFortune, but nothing obvious stands out that would reveal the flag. Let's try calling it from the web page. This code defines the getFlag functions, add a div to show results, and a button to trigger it, along with a click handle. Running it gives us nothing. Not very helpful. So I thought, what if the endpoint is vulnerable to timings attack? Let's test that idea. The code now has a different click handler. In it, we iterate over printable ASCII range and we pass that as an argument to getFlag method, measuring how much it takes to execute each call. Unfortunately, the timings didn't reveal anything useful. No signs of timing-based side channels. But we did notice something interesting. Among the usual 200s OK, we also got 404s and 500s. Most were boring, but one response stood out. Looks like we might have command injection. Let's try that route. Injecting ls shows us there's a file named flag. Trying cat file with pipe it through base64 just to be safe. One quick Python script later, and we've got the binary locally. Let's drop it into Ghidra again. The binary is short. Main just checks whether we have passed the correct secret. That leads us to the isFlag function. Here is the version we've already applied some renaming. It does few things. First, it checks the input length. It should be 30 characters long. Then, it extracts the 1753 from the prefix. Finally, it does per character validations. Since we have the binary, let's go dynamic and fire up GDB. We can start the application providing the fake flag and put a relative breakpoint at 1586. Once the breakpoint is hit, we can check the AL register, that's called our first character, and under the RBP-0x25 is the calculated value. We can set the AL to the calculated value and continue. and we hit the breakpoint again. Now we can automate that. We run the binary again and set the same breakpoint as before. Now this is something new. We type commands and we'll provide commands that will be executed when the breakpoint is hit. First, we'll just limit some output that GDB prints, and then we set the variable c to be equal to generated flag character. We print it, and then we set al to be equal to the generated flag character so that we can continue. Next, we actually execute continue, and that ends our command sections. Now we just need to set some workaround for the pawn debug with the GDB, and we can continue execution. And that gives us the flag. Final result? Not bad for a fortune cookie. So, to wrap it up, this challenge combined WebAssembly reversing, some light JavaScript analysis, and ultimately a bit of command injection plus dynamic binary analysis using GDB. A neat mix of web and reversing, and a great example of thinking across the layers.